You've sat in traffic behind orange cones 100 times. You've watched crews tear up the road and wondered what's taking so long. Maybe you've cursed under your breath, checked your phone, and inched forward another 10 feet. The brake lights stretch ahead of you as far as you can see, and somewhere in the distance, machines are doing something to the road surface. But you've never actually seen what's happening on the other side of those cones. You've never understood why it takes so long, or what kind of equipment is responsible for all that noise and dust. A single machine is eating the road, literally grinding it to dust at 10 feet per minute, swallowing asphalt that's been sitting there for 20 years, and spitting it into dump trucks trailing behind. The cutting drum screams at 120 RPM, while carbide teeth chew through pavement like it's nothing. And the craziest part? That old road you're watching disappear is about to become the new road. The same material, recycled and relaid, sometimes within the same week. This is the cold planer, and once you understand how it works, you'll never look at road construction the same way again. The official name is a cold milling machine, but operators call it a cold planer, a profiler, or sometimes just the mill. And while the name sounds simple, this machine is one of the most sophisticated pieces of equipment in the entire construction industry. The Wirtgen W210i is the industry workhorse. 800 horsepower packed into a machine that weighs over 40 tons. It can cut a path 7 feet wide and up to 14 inches deep in a single pass. That's enough to remove an entire road surface down to the base layer without slowing down. Caterpillar makes the PM620, which runs similar specs. Roadtech builds the RX700 series. But regardless of manufacturer, the fundamental engineering is the same. A massive cutting drum, a conveyor system, and a grade control package that makes surgical precision possible on a machine that could crush a pickup truck. Now, you might think removing old asphalt is simple. Just scrape it off, right? But the physics involved are brutal. Asphalt isn't soft. It's a composite material, aggregate rock bound together with bitumen that's been baking in the sun and bonding with itself for decades. Tearing it up requires serious force applied in a very specific way. That's where the cutting drum comes in. And this component is where the real engineering lives. The drum itself is a steel cylinder, typically 6 to 7 feet wide on a standard highway machine. Some models run drums over 12 feet wide for major interstate projects. But the width isn't what makes it work. What makes it work are the picks. Hundreds of individual cutting picks stud the surface of that drum in a precise spiral pattern. Each pick is a small cone of tungsten carbide, one of the hardest materials on Earth, brazed onto a steel holder. As the drum rotates at 80 to 120 RPM, each pick strikes the asphalt surface and chips away a small piece of material. Multiply that by 200 picks hitting the pavement several times per second, and you start to understand the violence happening at the contact point. A single drum holds anywhere from 150 to over 200 individual picks, depending on the machine size and application. Each pick costs between $5 and $15. And here's the thing that surprises most people. These picks wear out constantly. On a major highway job, operators might replace 30 to 50 picks per shift. A full set of picks runs $2,000 to $5,000, and on a big project, you might burn through several sets per week. The pick pattern isn't random either. Engineers spend considerable time designing the spiral arrangement to ensure even material distribution, minimize vibration, and prevent the drum from developing grooves or uneven wear. Get the pattern wrong, and you'll see it in the finished surface. The milled pavement should have a uniform texture with consistent groove depth. That texture actually matters because it helps new asphalt bond properly when the paving crew comes through. But the cold planer doesn't just destroy the road, and this is where the story gets interesting. Watch a milling operation closely, and you'll notice a conveyor belt running from the cutting chamber up and over the machine to dump material into trucks running alongside or behind. That material has a name. It's called RAP, Reclaimed Asphalt Pavement. And RAP is worth money. The asphalt you're watching get chewed up contains two valuable components. First, the aggregate, which is just crushed rock. Second, the binder, which is asphalt cement, a petroleum product that's expensive to produce and transport. When the cold planer grinds up old pavement, it recovers both of those materials in a form that can be directly reused. In the United States alone, contractors mill over 100 million tons of RAP every year. And here's the number that matters. More than 90% of that material gets recycled back into new pavement. This isn't downcycling into lower-grade applications. This is direct reuse. The same road, ground up and relaid, often with better performance characteristics than the original. The economics are straightforward. Virgin asphalt materials cost significantly more per ton than incorporating RAP. Depending on oil prices and regional factors, using recycled materials saves $3 to $5 per ton. On a highway project that might use 50,000 tons of asphalt, that's $150,000 to $250,000 in material savings alone. For state departments of transportation managing thousands of lane miles, those savings add up to tens of millions annually. This recycling efficiency didn't happen by accident. The modern cold planer is specifically designed to produce RAP at a consistent gradation, meaning the particle size distribution is controlled so the recycled material behaves predictably when mixed into new asphalt. The cutting drum speed, the travel speed, and even the pick pattern all influence the final RAP quality. Operators adjust these parameters based on what the recycling plant needs. So while you're sitting in traffic, frustrated at the delay, you're actually watching one of the most efficient recycling operations in any industry. The environmental math works out dramatically in favor of milling and recycling versus traditional demolition and disposal. Less material goes to landfills, less virgin aggregate gets quarried, and less asphalt binder needs to be refined from petroleum. Now, here's where things get genuinely impressive from an engineering standpoint. That 40-ton machine eating the road isn't just chewing randomly. The cutting depth is controlled down to the millimeter, and I mean that literally. Modern cold planers use grade control systems that would rival precision surveying equipment. Working calls their system Level Pro. Caterpillar has Grade. Both accomplish the same goal. They maintain cutting depth with accuracy measured in fractions of an inch, typically within 1 to 3 millimeters of the target depth. Think about that for a second. A machine that weighs as much as a loaded semi-truck, spinning a drum covered in carbide teeth, and it's holding tolerance that you'd expect from a machine shop. The system uses multiple reference points. Sonic sensors bounce signals off the unmilled surface or off a string line set up alongside the work zone. Some setups use laser references or total stations. The most advanced systems use GPS with real-time kinematic correction, achieving centimeter-level positioning anywhere the machine operates. Why does this precision matter? Because modern road design specifies surface profiles down to the fraction of an inch. If you're milling a road to prepare for an overlay, you need to remove exactly the right amount of material. Take off too little, and your finished road surface ends up higher than the curbs and drainage structures. Take off too much, and you've wasted material, time, and money. The precision also matters for ride quality. Vehicles are sensitive to surface irregularities. An inconsistent milling depth creates waves and bumps that translate directly into uncomfortable driving conditions and accelerated vehicle wear. The goal is a surface that's flat enough to meet International Roughness Index specifications, which are measured in inches per mile of vertical deviation. Operators manage all of this from a control station that looks more like an aircraft cockpit than a construction vehicle. Multiple screens display real-time cutting depth, cross slope, material flow rates, and system diagnostics. The operator can adjust parameters on the fly, responding to changing conditions or specifications as the machine progresses down the road. Now let's zoom out and look at what a full milling operation actually involves. Because the cold planer doesn't work alone, a typical highway milling job runs as a convoy. The cold planer leads, obviously, but behind it, you'll see 3 to 5 dump trucks rotating in and out in a carefully choreographed sequence. As one truck fills with RAP, it pulls away and an empty truck moves into position. This exchange happens without stopping the milling machine. Downtime costs money, and the goal is continuous production. Every minute that drum stops spinning is money lost. Behind the dump trucks, you'll usually see a sweeper. The milling process leaves loose debris on the freshly cut surface, small fragments that didn't make it onto the conveyor. The sweeper clears this material to prepare for whatever comes next, whether that's paving, inspection, or temporary traffic. A water truck often runs with the convoy as well. Water serves multiple purposes. It suppresses dust at the cutting zone, which matters for worker health and public nuisance reasons. It also helps cool the cutting picks, extending their life and maintaining cutting efficiency. On major projects, you might also see a skid steer or small excavator handling edge work. The cold planer excels at large open surfaces, but tight spots around manholes, curbs, and transitions sometimes need handwork or smaller equipment. The production rate depends on a lot of factors. Cutting depth, material hardness, machine size, and traffic control complexity all play a role. But a reasonable estimate for highway work is 1 to 3 miles per day. Urban work with frequent obstacles and shorter runs produces less. Rural highways with long, uninterrupted stretches can push higher numbers. The cost side is equally variable. Milling contractors typically bid projects at $1.50 to $4 per square yard, depending on depth, access, and local market conditions. That price includes the machine operation, trucking, labor, and all the supporting equipment. Let's put some real numbers on this. A standard 12-foot lane, milled 1 mile, represents about 63,000 square feet. At $3 per square yard, that's roughly $21,000 per lane mile. A 4-lane highway project running 10 miles costs somewhere between $500,000 and $2 million just for the milling phase, before any new asphalt gets laid. When you factor in the value of the recovered RAP, the economics shift further. That recycled material often goes directly to a hot mix plant where it gets incorporated into new asphalt at ratios ranging from 15 to 50% RAP content. The material value offsets some of the milling cost, though typically the contractor captures that value rather than the road owner. So the next time you're stuck behind those orange cones, watching the road disappear and cursing the delay, consider what you're actually witnessing. You're watching a 40-ton machine hold millimeter tolerances while spinning 200 carbide picks at 120 RPM. You're watching a recycling operation recover materials worth millions of dollars annually. You're watching technology that took decades to develop, operating at the intersection of mechanical engineering, material science, and precision control systems. The road you drove on this morning might contain material that was milled up 5 years ago, 100 miles away, from a road your parents drove on. That's the cycle: destruction and rebirth. Old roads becoming new roads. The same aggregate and binder, reconfigured and relaid, carrying the next generation of traffic. The operators running these machines know exactly what they're doing. They manage a process that balances brute mechanical force with precision measurement, destructive power with environmental responsibility. They coordinate convoys, monitor equipment, replace worn picks, and deliver finished surfaces that meet specifications measured in fractions of an inch. Those orange cones you hate? They're protecting the most efficient recycling operation on Earth. And the machine doing the work is eating roads alive, one pass at a time.